this is what's out there. It's a representation of your cast iron boilers. And they haven't changed very much in the last 50 or 60 years. They've gotten a little bit smaller, not a lot. They all pretty much weigh the same. They all pretty much have the same amount of water. They all work the same way. The only difference is the color of the jackets. So we kind of call them low-tech because they're not very smart. The typical boiler of yesterday isn't very smart. It's just a dumb boiler, and it works. It does what it's supposed to do. Now, as of last September, boilers got a little bit smarter because the DOE mandated that there had to be some type of device, some type of control that will modulate the temperature of the boiler, whether it be outdoor reset or some type of inferential control, which will change the BTU output of the boiler directly proportionate to the load. So boilers have gotten smarter since last September. But what about all those boilers prior to last September? They're all pretty dumb. So what we've seen in the last few years is this explosion of rebates and incentives, and they're coming at us from everywhere. The government was throwing money at people. The utilities are still throwing money at people to get people to rip out these boilers and put in some new high-tech piece of equipment. And that's what has been the thrust lately. We saw a feeding frenzy a few years ago. I believe it was at the end of, if I'm not mistaken, it was the end of 2010, or either 10 or 11, I forget which, but it was when the rebates were, the government rebates were running out. And people, there was a feeding frenzy. And people just, they're putting boilers in because they were going to get $1,500 back from the government. So, and then they were putting them in some places where maybe they shouldn't have. So that's really what we're going to talk about today, is this is what's going in. Here's your to boilers of today, a pretty good representation of high-tech condensing boilers. So again, those boilers are components. So what are we connecting them to? These boilers are going in houses that already have heating systems. So we're taking out one component that was more or less designed around the emitters that are in the house, and we're putting something in that works, but does it work as well as it should? What are we connecting them to? This is what we're connecting them to. Probably in the Northeast, this is the predominant form of heat emitters, is baseboard. We've got cast iron radiators, we've got radiant, but most of your heating systems are baseboard because they're easy to install, they're inexpensive, and compared to your other forms of emitters. So this is what we're hooking them up to. Well, the problem with that is that the baseboards are rated to operate at 180 degrees, and you can see by that red column that that's your BTUs per foot, 550 BTUs a foot at 1 gallon a minute, and 580 BTUs a foot at 4 gallons a minute with 3/4 inch baseboard. And if you have a vastly oversized baseboard system, I mean greatly oversized, then a condensing boiler will work pretty well in there. But look over in the column over on the left underneath the red arrow, 110, 120, 130. Now these are your ratings for condensing boilers, and this is where your condensing boilers work the best, and look at those BTU numbers. A big drop-off from the 550 or the 580. So basically what this means is that, again, unless your system is vastly oversized, in the dead of winter, when you're in those months when you're using the most amount of fuel, that boiler is going to be running upwards to 180 degrees. Well, obviously not condensing. You'll condense in the shoulder seasons. You'll condense pretty well because you don't need the BTUs. You don't need as many BTUs in the fall and in the spring. But in the dead of winter, those months where you're burning the most amount of fuel, you're not condensing. So it's basically, it's like putting a round peg in a square hole. It just doesn't work. It just plain doesn't work. It works some of the time, but in the case of this picture, that doesn't work at all. So here we go. Here's the story, that you've got to get your return water temperature below 135 degrees. That's where your condensing starts. The process begins at 135. And as that temperature goes lower than that 135, the condensing efficiency increases. So the lower you can get that return water temperature, the higher the amount of condensate is pulled out of the flue gas, and your combustion efficiency increases, and now you're getting up into the 90 range. But if it doesn't, then your actual operating efficiency is about where you'd be with a typical modern non-condensing boiler, and that's in the mid-80s. And you can do that with just about anything today. You can get to the mid-80s without even trying. So here you are. We're putting in this equipment that's supposed to deliver great savings and supposed to work really efficiently, and it will when you're not burning a lot of fuel. But when you're in the high fuel burning months, it's working like anything else. That's the sad truth about what we're trying to do. This little chart really shows that you're almost at a flat line in that non-condensing mode. That condensing process starts at that 135 degrees, and that curve raises sharply the lower that water temperature is, that return water temperature. If the water going into that boiler, the lower we can get it, that efficiency increases drastically. And even if we can get that return water temperature down to, say, 110, that puts us up here at about 92%, which is pretty darn good. Again, it's what are we hooking this up to? Now here's something that's been around for over 30 years. This is called heating edge perimeter heating. We don't even like to call it baseboards, perimeter heating. But you can see the difference. It has two pipe design. It has larger fin surface, and the fins are serrated. So what happens there is that acts like a scrubbing washboard, where it actually scrubs more BTUs out of that water that's passing by on your two pipes. And it looks like it has a nice look. It looks like baseboard. Here it is installed in a home, and it installs pretty much the same way any other baseboard installs. It was designed to give you more BTUs per foot at 180 degrees, and you can see that the best scenario is two supplies in parallel, and at 180 degrees over there in that 180 degree column, at 4 gallons a minute, you're putting out 1,115 BTUs, which is roughly twice what you get from standard baseboard. But we're talking about a component that matches up really well with a condensing boiler, and that's what's inside the circle. So we go over to the 140 degree average water temperature, the 130, even if we can get it to 140, which it should be fairly easy with a 20 degree delta T, we're looking at either 546 or 626, either 1 gallon a minute or 4 gallons a minute. If we get it down to 130, 516 BTUs a foot, which is basically right what you get with standard baseboard. But now you've got a product that's matched with that boiler that is going to condense. Now you're going to condense like crazy. It'll work really well in the shoulder seasons. You'll be your actual return temperature could be down in the 110 degree range because you don't need as many BTUs. But in the dead of winter, when you need all the BTUs you can get, your boiler is still going to condense. So again, it's really all about components. Now, if we've got a radiant system, this is a perfect match for a condensing boiler. Perfect match, because most radiant systems run on fairly low temperatures. Either above the floor or below the floor, we're looking at temperatures maxing out at about 140 degrees for our radiant system. Now, the next picture is going to, we're talking about a fairly high-tech type of system. Radiant systems are reasonably high-tech. What most people do is put a low-tech mixing valve in. Mixing valve, the thermostatic mixing valve, is low-tech. It does one thing, it does it very well. It lowers the water temperature to your set point. And that set point is a design temperature, so it does it all the time, no matter what the outdoor temperature is. Well, here's a high-tech component. There's a high-tech mixing valve. It's a computerized mixing valve. And it looks at temperature outside, it looks at the temperature of the water, and it makes a decision on how to adjust itself. And it will adjust itself based on the outdoor temperature. And as you can see, if a typical example would be 130 degrees water temperature at 0 outside, which puts us at the 0.8 line. And what that means is that every temperature degree increase outside gives you a 0.8 degree water temperature decrease inside. And the math that's involved is, as you can see over on the left, it's the mixed design minus the indoor design divided by indoor design minus outdoor design. And there's the 130 minus the 72 divided by the 72 minus 0, 58 over 72. It comes out to 0.8. So it's pretty simple. And if you follow that line down, you can see that as the temperature outside increases, the water temperature decreases also. So very simple. It's like having somebody in the cellar adjusting that mixing valve 24 hours a day. It's a high-tech component. So let's look at some more components. Let's take a look at some more components in the heating system and see what we can do to make that system better. Air is the enemy of the heating system. Absolute enemy of the hydronic system. We need to make it go away. It does all kinds of things, and they're all bad. It creates noise. That's that gurgling sound that you can hear in baseboard. It's like a waterfall all the time. It creates corrosion. Sure, it does. We've got iron, we've got steel, we've got water, and we've got air. Well, there you go. There's a recipe for iron oxide, and that's what's floating around inside that system. It will create flow issues. In fact, too much air will stop the flow entirely. So it creates flow issues, and it will decrease the system efficiency, because if there's air in the pipes, that means there's less water, and that water is now disconnected from a portion of that pipe, and it's not transferring the BTUs like it's supposed to. So that overall system efficiency has decreased because of air. So we need to make the air go away, and we use one of these things. We use them because we've always done it that way. We've been using them for years. They don't cost as much, and they work. They pretty much get the job done. So we've been using pretty low-tech equipment for a long time. And they work. They're basic. They're very simple. There's no moving parts whatsoever to them. You've got a little vent on the top, which vents the air to the atmosphere. We've got a place on the bottom, a connection for the expansion tank. And it works simply by moving that air upward, and that happens with these little vanes, which deflect those air bubbles into the upper chamber where they're vented out. However, those bubbles need, the water needs 18 inches of straight pipe to create that laminar flow, which makes those air bubbles rise to the top of the pipe. So it takes 18 inches of straight pipe. Now those bubbles are riding up on the top of the pipe, and they get vented out just like they're supposed to. But we've always done it this way. And this is a very typical picture. I know that's going to be very familiar to a lot of you. I'm sure you see it all the time. It's done all the time. Not even close to 18 inches. That's probably about 3. So basically, that air scoop is a coupling, and the air bubbles just fly right by, go through the system, come back around again, and fly right by, and basically it's not working. On the right is a high-tech air separator from about 30 years ago. Really great product, a great idea. It's been around for a little over 30 years. It's called a spiral vent. It works really well. It does not require the 18 inches. It's not directional. On the left is Taco's version, which is an improvement. It's the second generation of a very good idea. It's called the 4900 air separator. And you can see the difference just in the shape alone is different. One of the things on spiral vent is that they leak a lot, and guys have sent me pictures from the field of very creative ways to stop the leak. Here's one. A guy installed a ball valve in the barrel. There's another guy that got very creative with several fittings and a high vent just to get rid of the air. I'd say they've done a few things, but they all leak because there's no shutoff valve. There never was. There's no shutoff valve in the barrel. So Taco has done a better job, and they've improved on a really good idea by making it cone shaped, so there's no water up there in the top half where the mechanism is dry. So that's good. And it removes 3 times more air than a spiral vent. Impervious to glycol because of the stainless steel pawl ring, so glycol is not a problem. No minimum pipe run. You can put it right up against the elbow if you want. You don't have that 18-inch minimum. And those pawl rings create such a large surface area that separates all the air. So it's a pretty good component. And most importantly, it has a little shutoff valve. There's a little needle valve in the barrel, so it has a shutoff valve. So it's some improvements over a really good idea, and that was that spiral vent. Again, 30-year-old high-tech. We've seen these. They're low-tech.
Hey, Bruce, I'm going to jump in and just...
Go ahead.
Yeah,
Yes,
I'm just going to jump in and just do a status check with everybody. How are we doing? How's the pace? Are we doing good? And if you have any questions, gang, just type them on in, and we'll address them as they pop up. So I just wanted to make sure everything. Just let me know if we're doing how's the pace, etc. We'll continue to move on. But again, be able to just type in your questions as they come up, and we'll answer them as they come up. You may proceed. I'm done.
Okay. If you have a question, just absolutely type it in, and John, just jump in and stop me, and we'll answer that question. So here's low-tech 3-piece circulators. Been around for years. B&G, Takeo. There were several more that don't exist anymore, but these were the popular 3-piece circulators. Very high on maintenance, bearings to oil, couplings to brake. Here's high-tech from 1963, probably before most of you were born. High-tech in 1963, the first wet rotor circulator. Low-tech, it's a combination. Low-tech, low-tech, low-tech. You got a little 007 in there somewhere. That's high-tech from the 70s, and they're still out there. 007s came along in the early 70s. It took a while for them to be accepted by the industry because we as an industry don't jump onto anything. We're not early adopters at all. We want to let the other guy try it out for 10 years, and then if it works, then we'll jump all over it. But high-tech in the 70s. Flow checks, integral part of a heating system, pretty low-tech. One little moving part inside, very necessary item in a hydronic system. Well, now today's higher tech idea is to incorporate the flow check in the circulator. So we see that pretty much across the board. We've eliminated the fitting, and it's just a more efficient way to operate. And now, while we're talking about zoning, we've got a couple of things that we can do, a couple of ways that we can do it. We can do it with circulators, or we can do it with zone valves, and there's a 50, 55 or so year old idea. Works pretty well. Here's a new one, high-tech zone valve. This is one of the pictures that was sent to me. This is a circulator farm. It's always the one in the middle that breaks down. It's funny how that happens. That clean one in there is the one that failed, so they send the 200-pound guy to fix it. Here's a zone valve tree. So people get very creative with their zonings. So zone valves, again, low-tech, high-tech. I don't like to compare too much the Zone Sentry to the 571 because it's two different technologies. It's two totally different technologies. The 571 is a heat motor, and the Zone Sentry is a motorized zone valve. I would prefer to compare it to other motorized zone valves like the Honeywell. And that's fairly low-tech device. It's just a motor, a ball and an arm with a motor that moves the arm out of the way. And I did a little comparison on power consumption, opening time, CV, shut-off pressure, and you can see the difference. But most importantly, it is just a ball on an arm that moves out of the way. And the Zone Sentry is a ball valve. It's a true ball valve. If you took that head off and put a handle on there, you would have a ball valve. Compare it against these guys. Same thing. It's just a different jacket. It's basically the same thing. It's a motorized valve with a paddle instead of a ball. So we stack up very well against other motorized valves. There's nothing like this in the world, and it's the newest zone valve in the world, and there's nothing that compares to it. It's called the Zone Sentry, and it's not directional. Ignore that A and the B. It doesn't matter. You can pipe this any way you want. There are no rules with this. It's kind of refreshing. There's something with no rules. Do whatever you want. Pipe it any way you want. Upside down, vertical, horizontal, A, B, doesn't matter. So we're back to these condensing boilers. What can we do? Are we going to take those out? Are we going to take out those cast iron boilers and put these in? Are we going to go along with the rest of the herd? Because that's what your competition is putting in. Everybody wants to put these things in, and that's what they're doing. So you're going to go along, you're going to be like everybody else, or maybe be a little different. Maybe separate yourself from the herd and be a little bit different and offer those consumers maybe a more attractive alternative. Not everyone can afford the high price tag of that boiler changeout. let's face it, it's a pretty expensive proposition. And not everybody has that kind of money. So they've got that boiler that's not that old. Look at that 5-year, 10-year, 15-year-old cast iron boiler. Is there anything wrong with it? It doesn't leak. Works pretty well. It's just dumb. It's a dumb boiler. It heats up to every time that thermostat calls, it heats up to the maximum temperature. And when the circulator comes on, it runs as fast as it can, and it shoves those BTUs out into the system as fast as it can. There's no intelligence there. Well, what can we do? Can we make it better? Absolutely we can. And we can make these boilers better with products that are made right here in the United States. We don't need to go to Europe. We can do it with products that are made right here. So let's see, what can we do? Well, we could do this. Outdoor reset. That dumb boiler doesn't know the difference between a nice cool fall night or the coldest winter day, and so it's going to work like it's the coldest winter day. That's basically what we're going to do. That's how it's going to run, just like that. It doesn't know the difference between those two. Now, a new idea? No. Here's old high-tech. It's the Enetrol. Some of you old-timers that are out there might remember this. That was from 1976. Outdoor reset, Enetrol, 1976. Taco thought it was a pretty good idea, too. And a couple of years later, they modified the Enetrol into a product called the Mastermind. And it worked pretty well. They added a timer to it so that it would work on those boilers with tankless coils. Let's see, I see a question out here. Let's see, we have a question. Zone Sentry, do they have, what's that question? Bidirectional. Do they have a direction for installation? No, they don't. It'll go either direction. And
right, yeah, it can be installed in any direction.
Right, any direction. Upside down, vertical, horizontal.
We got a question also. I'm sorry, I didn't mean to speak over you there, Bruce. Travis Gilbert asked, can the Zone Sentry be used on solar thermal applications?
Solar thermal. What's the? I think you can get pretty high temperatures on a solar system, but on solar thermal, let me think about that for a minute. I'd have to see what the max temperature that it can handle is.
Yeah, my gut reaction on that is yes, it can. Probably the geothermal version because it has corrosion-resistant components. Yeah,
it would be corrosion resistance important, and then temperature that it'll operate at, because you can get some pretty high temperatures in solar systems. So.
Well, I'll look that up while you continue.
Okay. So the Mastermind.
It's great teamwork, isn't it?
Mastermind, old high tech, been around again, since 1978. So that's a long time. So let me see, where are we going next? So here's new high tech, brand new product, not even a year old, is the Fuel Miser, model number SR501OR for outdoor reset, single zone switching relay. Basically, we're going to put that between our dumb boiler and whatever was telling our dumb boiler to turn on. That's probably the easiest way to explain how this is going to work. We've got something is making that boiler go on. It's a thermostat is operating a relay, which is then operating an end switch, which is going to the boiler, or we've got zone valves. We have something that's telling that boiler to turn on. Well, we're going to put this in between there. So we're going to, whatever was telling that boiler to turn on is now going to hook up to this, and then we're going to go from here to the boiler. It's very simple, needs 120 volts to work. We've got connections for the thermostat, or again that end switch, whatever was telling the boiler to start up, and we have a connection for the domestic hot water, so that if we have an indirect, when that indirect calls, then we're going to override that outdoor reset. We have a terminal for the circulator, line voltage terminal for the circulator. So in some cases we need to take the circulator off the boiler control and put it on here. Case in point would be if we were operating with zone valves and we had a control on the boiler that would start the circulator. Well, we're going to turn the boiler off. We don't want to turn the circulator off also, so we wire the circulator over here. And then we have a couple of terminals. There's our TT, goes over to the boiler, and a couple of terminals for our indoor sensor and the outdoor sensor. The outdoor sensor goes on the north side of the house. It goes in the shade. It goes above the snow line if you live in a climate that gets snow, and it needs to be installed any place where it doesn't feel heat. Your indoor sensor goes on the supply pipe leading out of the boiler. And it's very, very simple. It's a strap-on. It can be installed in a well if you have a well, but the idea is that it would strap onto the pipe. And then we have to tell it what to do. We have to give this its adjustment, and that's pretty simple. There are three little dip switches. One of them will, dip switch 1 will, in the on position, gives you 140-degree minimum. Because remember, we're installing this on a cast iron boiler, so we do not want it to condense. So we can put a threshold at 140. However, if you're installing this in a ModCon that for some reason doesn't have outdoor reset, I know most of them do, but suppose that function stopped working. Well, you could turn that switch off, and now it would allow the system to modulate down to 70 degrees. We have a differential switch, 20 degrees or 10 degrees. 20 gives you a longer off cycle, which is desirable. And then the third switch is for pump operation. On is with heat or a domestic hot water call, and off is heat only. And then finally, we need to tell this at what outdoor temperature we want 180-degree boiler water. So we set that little dial is set from -30 to +40. And my suggestion to people is set it at +10. And +10 outside is pretty much you need hot water. So put it at 10 in its program, and it could not be simpler. So with just this one device, we've raised the intelligence bar on that dumb boiler. Taco offers a great little piece that is designed for the heating oil and propane customer, because those are the expensive fuels today. And it just talks in homeowner language about what this will do for you. And one of the things that it brings out is that a study was done a few years back, and it was done in Minnesota, which I think John will corroborate this, has arguably some of the worst weather in the country. It's either too hot or too cold.
Especially this spring.
Yeah, really. Like this is not a spring. This is just a long winter that you've got.
Right.
But it showed that installing this in an existing boiler saved an average of 14%. So typical payback is anywhere from 1 to 3 years. So that's a really great selling point to the homeowner. So these pieces are available, no cost from Taco. So just contact your rep, and they'll get them out.
Hey, Bruce, I have a couple more questions up here, and
Sure.
an answer to a couple. As far as the Zone Sentry on solar thermal, the maximum temperature rating for the Zone Sentry is 220 degrees.
Okay.
Maximum ambient is 135, so we'll have to see how that would fit into your particular application.
Okay.
We also had another question about a three-way Zone Sentry, and yes, we do have a three-way Zone Sentry. And if you check your answer rundown there, I did include a link to the submittal data sheet for that three-ways for the Zone Sentry, so you can get the information on the three-ways there as well.
That's a new product from this year, I believe. That's just that's new in the past few months.
Right. Yeah, it is fairly recent.
Yeah. Yeah. So great. Good answer. Okay. So let me see. Where are we here? Okay. There's that. Did I go backwards? I did. Oh, I'm going the wrong direction. What's going on here? I'm clicking the wrong arrow. You'd think I'd know how to do this by now. There we go. So what else can we do here? What else can we do? We've raised the bar a little bit on that boiler. We've made it a little bit more intelligent. What else can we do with this? What else can we do? Well, one of the things we can possibly do is put a variable speed pump in. So what do they do? You know, one of the questions out there is, well, why do we do it? Why do we put one in? Well, they vary their speed based on changing loads, and the external information they use can come from a couple of different places. Your best applications are systems with zone valves. You'd have one circulator and multiple zone valves, or a single circulator with a radiant system in multiple zones on a manifold using actuators, which are nothing more than zone valves. Those are your best applications. It's not advisable to do individual circulators with variable speed pumps, although it can be done. It's just the better way to do it is with the zone valves. It's just a more cost-effective way to do it. We've had people that do it. They put in the individual circulators, and it works just fine. It's just if you're looking to maximize the efficiency of the system, one of the ways that you want to improve the efficiency is electric usage. And one circulator and multiple zone valves is going to use a lot less electricity than multiple circulators. So the idea, again, my suggestion is to go with zone valves. Those are your best applications. Here's our offering. We have the VDT pump on the right, the VDT circulator, which is a standard 00 series circulator with a microprocessor. And on the left is the Taco's version of the ECM motor. It's called the Bumblebee. And this is also a variable speed pump, and it does a little bit more than the VDT pump. The VDT pump does one thing. The Bumblebee does several. And again, it has an ECM motor, so from an electrical standpoint, it's way more efficient than the VDT pump from an electrical standpoint. Perfect combination is a variable speed pump and zone valves. It's an absolute perfect combination. We have a new program called the Zoning Revolution, and this is part of that. Is your best scenario is a Bumblebee and zone valves. It's a great addition. Now, again, this can be added to that existing system. That existing system out there may have zone valves already. Might already have zone valves in them. So we replace the zone valves with zone sentries. We replace the pump with a variable speed pump. You've just raised the intelligence bar of that system even more. And again, we haven't changed the boiler, but the boiler is going to be the recipient of this. The boiler is going to run more efficiently. The three modes that the Bumblebee operate in is constant power, where it becomes a 4-speed circulator. So we have 4 fixed speeds, and we can run it at that, and it gives you 4 different pump curves. We can do a set point mode where we will set that at a temperature that we want the pump to change its speed to maintain, and I'll show you a couple of examples of where these modes would work. And then we have the delta T mode, which allows a fixed system differential with a range of anywhere from 5 to 50 degrees. And again, typically a heating system has a delta T of 20, so typical baseboard system, we would set that at 20. The constant power mode, there's your 4 fixed speeds. It gives you 4 separate pump curves. So it's going to run on these curves, and you can see the range, and it becomes a 4-speed pump. And it doesn't change its speeds. You put it on that speed, it runs at that speed all the time, and you can make a case for that for a fixed speed pump. Here's a couple of examples where the set point might work. You could use that on the left, the top left, as an injection mixing pump. So you're using that as basically like to replace a mixing valve. Now we're injecting into our radiant system, and we're looking at temperature going out, and the pump speeds up or slows down to maintain that temperature. We could use it as a boiler bypass, or this is really thinking outside the box. We could put the sensor in the airstream of a fan coil and set that at the temperature that we want the air to be, and now the pump is going to vary its speed, and it's going to change the flow of the water going through the coil to match that air temperature. So you can do a lot. The set point doesn't care what the medium is. All it's looking for is temperature. Of course, in the delta T mode, the idea here is, again, radiant or zone valves. And we look at the supply water temperature, return water temperature. We set it for the delta T we're trying to maintain, and the pump speeds up or slows down to maintain that delta T. So what it does, the operation, we're looking at supply and return with our sensors. We've got it set for 20 degrees, and the pump comes on. It runs full speed for 3 minutes, and then it looks at those 2 points. And it's going to slow down if that delta T has shrunk, which invariably it will do. It'll slow down once it sees that delta T has decreased. So it's set for 20 and it's set the delta T is 7. It slows that flow of water down, spreads that delta T back out to 20. As the valves close down, the pump slows down. Now, if a valve should open up in this process, that return sensor feels that slug of cold water, and that delta T all of a sudden spread out from 20 to 25, 30, 35 because of that cold water. It speeds up to shove those BTUs back out into the system and get that delta T back to 20, at which point it slows back down again. What we end up doing is maintaining that 20 degrees across the entire system, which of course is the way the system was designed to operate. It ends up reducing noise in the system, and it smooths out the operation in that the boiler is off longer. We do not get short cycling of the boiler, which will happen with a fixed speed pump and a boiler that's running off of high limit. Because that fixed speed pump is running as fast as it can. It's shoving that water out there into the system as fast as it can. Boiler shuts off on limit, comes back on a minute or so later, runs for 45 seconds, shuts off, comes back on 2 minutes later. It's not an efficient way to run the boiler. The boiler that's off is the efficient boiler. So we get a longer on cycle and a longer off cycle, and the boiler is running more efficiently. Again, the boiler that's not running is not burning fuel.
Got a couple of questions here, Bruce.
Okay.
If we might throw those at him. A couple about going back to the fuel miser. I just want to address those for the rest of the group. One was from Sereno. It says, so the fuel miser only works in a one-zone application. How would a multi-zone application or multi-circulator application work? I just want to make sure everyone's clear on that. The fuel miser will work in a single-zone application or a multi-zone application. Whatever your end switch from your multi-zone multi-pump relay or from your zone valve control would go to the thermostat input on the fuel miser, and then the end switch from the fuel miser goes to TT on the boiler. So it just works as a go-between, whether it's one zone or a whole bunch of zones. That part doesn't matter.
Yeah, it's like I had said. I think that if you think about it in terms of this goes between your boiler and whatever was starting your boiler. Doesn't matter what was starting your boiler. Something was telling that boiler to turn on. And that wire, let's say there's a wire going to the boiler. It's coming from somewhere. We take it off the boiler, we put it on the fuel miser, and then we run a wire from the end switch and the fuel miser over the boiler. It's a go-between. That's a really good way to put it, John. A go-between.
There you go. Yeah, it's kind of like a mediator,
yeah,
so to speak.
Yeah. I think the only application, hydronic application, that it won't work on is a boiler with a tankless coil.
Right.
So because you have to maintain a temperature all the time in that tankless coil, so it isn't going to work in that application, but it'll work in everything else.
I have a bunch of questions on the Bumblebee, ECM motors, Delta T's, etc. But Bruce, I think I'm going to let you finish this part up, and then we'll address those, because I think you're going to address some of these questions coming up. Not all of them, but I think we're going to address some of them, so we'll let that go.
Okay.
But guys who put in your questions, we will address those, I promise you.
Okay. Then moving right along. Oh, go ahead. Oh, shall I go? Am I still on?
You're still on.
Okay. What we're trying to do with the Delta T pump is very simple. It's based on the universal hydronics formula, which is this. It's very simple. GPM equals BTU divided by this little formula, Delta T times 500. So GPM is gallons per minute. Our BTU-H is the load, and that's the load of the building. Delta T is the design temperature drop of the system, and if we've got baseboard, it's 20 degrees. Typically with gradient, it's 10 degrees. And that means that in worst case scenario, we're going to lose 20 degrees across the system. And the 500 is simply the weight of a gallon of water times 60 minutes. It's 8.33 times 60. So there's our formula. It's based on that. So we apply that to this technology. There's that formula again. So if we change the load, the GPM needed is going to change. Now that load, again, what we want fixed is the delta T. We really want that to stay the same. The 500 has to stay the same because that's a constant. If we change the delta T, that would do it too, but we don't want to do that. That happens right now with a fixed speed pump. The delta T changes all the time. So by speeding up or slowing down the pump, we accomplish this purpose. Let's change this formula around a little bit. So let's change it to this. BTUH, which is load, is going to equal gallons per minute times delta T times 500. So again, if we change the GPM, we change that output. That's what happens. That load changes every single minute of the day. You can have a situation where first thing in the morning it's 37 degrees and the load is that on the house. It's 37 degrees outside and the building is losing heat, so the load is based on that. And then by noon it's warmed up to 60 degrees, well, the load changed. The load on that building has changed. The BTU requirement for that building has changed in that amount of time. So the load changes constantly. By changing the GPM, we change the BTU output. Now again, if we change the delta T, that will do it too, but we don't want to do that. So the two things that we want fixed are that delta T and that 500. So the only way that we can change the load is by changing the GPM, and that is how it works. And it is so simple. It's laughable. It's just, why didn't somebody think of this years ago? Change the load by changing the GPM. Here's an example of high-tech pumps that are out there in the world today. And again, we're looking at pumps that change their speed based on external information. We've got the Europeans over on the left, and then we've got us in the middle and on the right. And the difference between them and us is very simple. It's how the systems are designed and the components that are in the system. In Europe, they don't have cast iron boilers, first off. They have mostly wall-hung modulating condensing boilers. They've done that for years. They have either radiant systems or they have panel radiators with thermostatic radiator valves. That thermostatic radiator valve is an individual zone valve mounted to the radiator, and it senses temperature right in the vicinity of that radiator, and it opens and closes based on the temperature in that area. They also have very small risers, mostly 3/8 tubes that are going from a supply pipe that's going around the perimeter of the building up into the supply and return to these radiators, little 3/8 pipes that have a pretty large pressure drop. So a delta P pump is going to react to pressure changes. So the pump is set for worst case scenario, which is all of these open, and as these valves close down, which they do, again, if the temperature in that area of the radiator increases, the valve closes, the pump senses a drop in pressure, the pressure changes, and it slows down to accommodate that. And the valve opens up, it speeds up. So basically, it's speeding up to fill a pipe with holes, fill a hole with water. You've got a pipe with lots of holes in it, and a hole opens up, and it speeds up to fill that hole with water, and it works perfectly. It's an absolute perfect application pump for that application. Perfect. And if that's what you have, that's the pump that you should use because it's the right component for that system. Let's come back across the pond. We're over here now. What do we have here? Well, we have all kinds of different boilers. We also have modcons, but we got cast iron boilers. In fact, there's more of them than there are modcons. But we mostly have baseboard. And we have 3 or 4 zones of baseboard, series loop baseboard. So if we take a component that's designed for many, many zones with high pressure drop, and we hook it up to a system that's 3 or 4 zones with a fairly low pressure drop, because baseboard doesn't really have much of a pressure drop. So a zone valve opens, there's a slight change in the pressure, but it's really not much. Basically, that pump works like a however many zones are open speed pump. If you have a 3-zone system, you've got a 3-zone pump. It operates at 3 different speeds, and that's it. The delta T pump works on temperature, and it speeds up and slows down based on the load of the system. And it's the perfect application for how we do things in this country. It's that simple. So let me take a look at the clock here. I think we're kind of almost time to start wrapping things up. When I Googled wrapping up, this is what came up. So how do we make...
Sure, that's where you got that picture, Bruce. Right.
Wrapping things up. Some ways that we can increase the boiler efficiency. Now, some of them are very basic, and some of them don't involve very much work. And one of them is, this should be very basic: keep the boiler clean. Keep the boiler clean, inside and out. And inside is is inside the boiler. And that really applies especially to these condensing boilers. There's a lot of things going on inside those boilers that you're not even aware of, that don't affect the cast iron boiler. They do affect the condensing boiler. But inside and out, keep it clean. That keeps the efficiency of the boiler at its maximum. Insulating the pipes is another good one. That's a very simple way of improving the system efficiency by not losing any more BTUs into the atmosphere or in the cellar or into the basement. Just insulating the pipes. Very, very simple way to make the machine more efficient. Tune up the boiler using electronic combustion analyzers. That should be a given today. That absolutely should be a given. Anybody that's working on boilers today that doesn't have one of these is living in the past. There is so much information that you need to know that you don't get from the old style wet kits that we've had for years. We need to know a lot more information today than we did in the past. And I like to equate using a wet kit to taking a snapshot. It's like gives you a snapshot of the conditions inside that boiler at any given moment in time. And that electronic combustion analyzer is a movie. It's a motion picture, because as you make an adjustment, you can see it instantly. You see exactly what's going on. So it's again, that should be a given with today's technology. What else can we do? Well, we could get into some high efficiency, low temperature emitters. Again, this is maximizing components. Low efficiency, low temperature, high efficiency emitters is the name of the game today. Everything is low temp, low temp, low temp. So that's where we're going to get the maximum efficiency out of our boilers, our condensing boilers, and it's matching it up with an emitter that is going to operate at the same kind of BTU output, but with lower temperature water. Add the outdoor reset control. Today, the condensing boilers, the ModCons, all have it. By adding the outdoor reset control to the existing boiler, again, you brought the intelligence level of that boiler almost up to the level of the condensing boiler. You know, you're really, when it's really cold at the dead of winter, the boiler is going to run like it always did. But the other, and I want to say 90%, maybe even more than that, in the mid 90% of the time, you don't need that high temperature water. You can get away with something less. Typically, we see design temperatures 5 to 7% of the heating season, design temperature, and that whatever area you're in, design temperature. For instance, where I live, it's 7 degrees, and it hit that probably, I don't know, 6 or 7 days. It hit close to that this winter. The rest of the time, it was not that cold. So by adding the outdoor reset, the boiler automatically adjusts its temperature to match that BTU load. There's no difference in temperature in the building. You feel the same, but the boiler's off, so it's more efficient. And then finally, changing your system to zone valves, multiple zones, and adding a variable speed pump. Again, the intelligence bar on the boiler has been raised, and now with the addition of the outdoor reset, the boiler is modulating its temperature, and the variable speed pump is following that. When we set that delta T at 20, it follows. The pump doesn't care what the temperature is. All it cares about is the differential, the 20 degrees. So it follows it. So if your boiler, instead of running at 180 degrees on a particular day, is running at 165, then the pump is looking at trying to get it down to 145. It's trying to spread that delta T out to 145 degrees. So we're taking less water out of the boiler. The boiler is off longer. And again, the boiler that is not running is not burning any fuel. Over the long run, the efficiency level goes up. We have a number. The number is 14% on the outdoor reset. And we still haven't quantified what the actual savings is with variable speed pump. I think we need a little bit more time for some research, but at some point down the road, somebody's going to put a number to that and say it's going to give you X. We'll have that, but we know that it will make the system run more efficiently, which means burning less fuel. We absolutely know it. We just don't have a number yet.
I've seen numbers. I've seen individuals, and I think one of them might be with us here today, who had saw his fuel consumption drop 15% in a harsher winter with the variable speed pump. And
Wow.
another guy who saw his customers' fuel consumption drop 33%. But those are extreme examples, and obviously your mileage may differ.
Mm-hmm. You know, but you're right. This was a tougher winter. The degree days were up all over the country. So, if you have a harsher winter and the numbers and you still show the savings, that's amazing. And if you take an average winter, the savings is going to be even higher. So, it'll be interesting to see what we end up with. What we can actually say. This you're going to get this for an average. So. How are we doing? How are we doing on those questions?
Oh, we have some really good ones. Let me jump in here. One was from Jim Price, and he asked this a while ago, and I wanted to hang on to it because it's such a good question. Is what is the electrical savings of a Bumblebee with an ECM motor versus a standard 007 pump? And that's such a common question, Bruce. And I think, Jim, the marketing department will tell you it's 60 to 85%. It'll use 60 to 85% less electricity, the Bumblebee or any ECM motor, compared to a standard fixed-speed circulator. That's what the marketing department will tell you. A calculator will tell you it's anywhere from $8 to $10 a year. We're talking about 1/25th horsepower circulators that don't use much electricity anyway. A 007 is like an 80-watt light bulb that doesn't run that you don't have on all the time. So the electrical savings is, I think it's a nice perk when it comes to any ECM circulator. In reality, it's going to be one of those things you don't even see in your electric bill. I mean, and that's not $8 or $10 a year, or not $8 or $10 a month, Jim. That's $8 or $10 a year in terms of electrical consumption, comparing one to the other. So I always bristle when guys say, the ECM circulators, the variable speed pumps are going to save a ton of money in electricity. They're going to save they're going to use a lot less electricity, but it doesn't necessarily translate into dollars on the residential end, dollars that'll matter much to a consumer. On a commercial end, when you're talking about 1 horsepower circulators and above, well, now the story starts to get a little bit different because those do use a lot of electricity. But in a residential application, the difference in electricity or electrical consumption, one pump to one pump, really isn't much. So I just wanted to make sure that's fairly clear. I hope that answers your question there, Jim. And Bruce, have you seen any similar scenarios?
Well, I know that if you look at just the wattage alone, a typical 00 is running about 80 to 85 watts, and on high speed, a Bumblebee is running at 40. So I mean, there's more than 50% reduction in the wattage, and it can run down as low as 9 on the low end. But so if you take an average of in between, sure, absolutely, it's a lot less electricity, but you're not burning much to start with. So I tell people don't brag too much about electric savings, because I think, John, you used to say you could get a movie and a popcorn. I went to the movies the other day and it was $12 to get into the movie. So, and that was without the popcorn. So.
Right. So yeah, that's what you could do with the savings in electricity. So I always urge people, guys will say, well, I've got 5 circulators at 80 watts. That's 400 watts. If I went to 1 ECM circulator and 5 zone valves, I'd save a ton of electricity. And yeah, you would. You might go from, say, $150 of electrical consumption a year to maybe 10. Now that's a lot of that's $140 annually. The point, however, is you could get almost all of the way there by simply going with 1 007
right.
and 5 zone valves instead of it being an ECM circulator.
Right.
And I hope that maybe I didn't word that right. The savings is going from 5 circulators to 1. It's not the ECM element. It's the 5 circulators to 1 circulator element that saves the most amount of money. So if you went like with 1 007 and 5 zone valves compared to 5 circulators, your annual consumption, electrical consumption to run that might go from $150 to $30. Swap out the 007 with an ECM circulator, that consumption might go from $30 to $10. Now so that's a $20 savings. Again, that's dinner. That's a movie by yourself with popcorn annually. So you make that call. The benefit of a variable speed delta T circulator is not in the ECM motor, it's in the delta T function. That's going to make, as Bruce said, that's going to make the boiler short cycle less and operate to its peak efficiency, and that's what's going to cut down your overall fuel consumption.
Yeah, that boiler is, again, by adding intelligence to that boiler, the efficiency level of the boiler, and it's not combustion efficiency. This is seasonal efficiency. This is how much fuel it's using. It's not how much of what percentage of the fuel is going up the chimney. This is strictly fuel alone. The boiler that is not running is not burning any fuel, and that's the key. That the boiler is not running as much. It does not run as long as it did before.
Okay. I'm going to bring in Anthony Reichow here. Anthony, I just unmuted you. Can you
Joe, John. I can hear you. Can you hear me?
Hi, Anthony.
We can hear Anthony. Anthony's the guy that had his oil consumption drop 15% with a variable speed pump. Could you elaborate on that for me a little bit, Anthony?
Well, I told you that I changed out my pump. I had a 007 on my system for years. I changed it out one night, just at the beginning of the heating season, to 008 VDT. And the winter was 15% colder that year. This is about 3 years now. I've had it for about 3 years. And we went from 2.5 tanks to a tank and 3/4 the first year just by changing out the pump. I mean, so, and I'm going to the place now where I encourage guys, if you're a guy who likes to do pumps, and we know we have an industry of guys that like to do pumps. They just have more confidence in pumps than they do in zone valves. Then put a Delta T circle on every zone.
Yeah.
Be done with it.
There you go.
You know?
Because the Delta T circulator will, in fact, vary its speed when used as a zone pump because the load changes. The Delta P circulator is just going to find its happy spot, and that's the speed it's going to run.
Yeah, everybody looks at that boiler efficiency, and Bruce, this is a great presentation. Everybody looks at the boiler. They look at that yellow tag on there. They look at that efficiency, and I think what we got to do is we got to broaden our scope of vision to look at all the other components which you talked about today. Getting the air out of the system, putting some intelligence on the boiler, making sure we have system flow that's absolutely proper. And if we do that, now we can really make a difference in a customer's life for 25 years.
And at a substantially lower cost than the competition. The competition is going out there selling them this new fancy high-tech boiler, and we can almost get to the same place by making what's already there a little bit better. And that's what I had said about separating yourself from the herd. And, you go in there with, well, look, I can do just as well, and it's going to cost you a lot less money. You got a good shot at winning the job.
Absolutely. Absolutely. It's good to hear from you guys. I'm glad I could be a part of this. And, John, thanks for the invite.
Hey, Anthony Reichow is the ace trainer for B.J. Taroni, the TACO rep down in Philadelphia, and the holder of the Fluffy Bumblebee for TACO Trainer of the Year. So,
good to hear from you, Anthony.
Hey.
Well, I'm anxious to give it up, guys. It's been a great weight to carry, but probably more responsibility than I deserve.
All right, Anthony. Thanks, bud. We got some more questions to get to. This is from Tom. Tom asked this question earlier, and again, it's a good one. I took out a single-speed circulator with a less than 2-degree delta T, put in a 3-speed, and at the lowest speed, the delta T went to nearly 21 degrees or so. Was I lucky? Does flow through a baseboard really matter? Absolutely, flow through a baseboard matters. And I think what you were seeing there, Tom, is the actual, real-world application of the universal hydronics formula, where GPM equals BTUH divided by delta T times 500. You had a heat load and you had a pump running. I'm sure that pump must have been oversized for the application. It's running at breakneck speed. In order for this to work, to deliver the BTUs, you need the delta T had to shrink to about 2 degrees. You were delivering the BTUs. So, yeah, the flow does matter. You were giving it such a high flow rate for this thing to balance out. The delta T went down to 2 degrees. So I'm guessing that was probably a fairly warm day for you too, Tom. Probably later on in the winter, that delta T might have spread out a little bit more. More zones were open. The delta T might have spread out a little bit more. The 3-speed circulator you had running at low speed, well, that was running at a much lower speed. GPM equals BTUH divided by delta T times 500. The BTUH was where it was. it might have been a colder day as well. So it all balances itself out. I guess the bigger point here, where flow rate does matter through a baseboard system, in that if we can keep that delta T fixed, the flow rate is going to change along with the BTU requirement. So we're always delivering the right amount of BTUs 99.9% of the heating season. The only time we're not is when that Bumblebee is running at its low speed, which might in fact be more than you need when it's really, really cold outside. So it does matter, but what you've seen there is the living personification of the universal hydronics formula. So that's why I wanted to hang on to your question and address it, because it's such a great point. It perfectly illustrates why a delta T pump is really beneficial. Think of that water going out at 180 and coming back at 178. Can you talk about a boiler short cycling like nuts? But if that water's going out at 180 and coming back at 160, well, that boiler and you've got a decent differential on your control, you're going to a lot of the time you're going to satisfy the call for heat without ever firing the boiler, and it doesn't get any more efficient than that. Then when the boiler does fire, it's going to have fewer firing cycles, but the firing cycles are going to be longer, and we get that seasonal cycle efficiency that Bruce was talking about. So that's a great, great question, Tom, and I'm really glad you brought that up. I hope that answered or addressed your question or your point. It really is an excellent one, and it gets right to the heart of the matter. Now,
also, can I just jump in? Is one thing to keep in mind also is the mass effect. You've got the mass of that boiler. You've got the weight of the iron. You've got all that water in there, and you've got all those BTUs that are stored in that boiler. So if we slow that flow rate down, we're not slamming all those BTUs out of the boiler as fast as we can. And again, we've got a storage, like a warehouse of BTUs. And by slowing that flow rate down, that boiler is off longer. And like you said, John, the burner might not even fire. We've used the fuel. Now we're going to use those BTUs that we've stored in that boiler, and we're going to slow down that flow going out to the system.
Right. We've already paid money to make the BTUs. Why pay money to make them again? Let's use what we've already created. Exactly. And to follow that up, Matthew Reed had a really good question. Would there be any benefit to increasing the delta T, slowing the pump, and saving energy? Or would that be counterintuitive, as the system would need to run longer? Again, if we're looking at electrical savings with the pump itself, no, it doesn't make any difference. Again, you're talking about pennies. That's not really the issue. If you've got a lot of mass out in the system, like big old cast iron rads or cast iron baseboard, there might be a benefit to increasing the system delta T to maybe 30 degrees. As long as your average water temperature is what it needs to be to deliver the BTUs, there certainly might be a benefit to that. Take advantage of the mass of both your boiler and your delivery. Again, as Bruce said, look at the system as a system, not just this part being thrown into that system. What do you have on the delivery side? What do you have on the creation side? And how do you get the BTUs from the creation side to the delivery side effectively so everything works happily? And we had another question. This is from Curtis Reynolds. Upgrading an old system to any ECM motor will cause metal filings to attach to the pump. How do you recommend this problem? That's the interesting thing about ECM. ECM stands for electrically commutated motor. Basically, there's a permanent magnet inside the rotor that gets this thing to work. And the concern with ECM pumps in the U.S. is on the big metal filings, things like that on the low is part of the problem. The bigger problem is black iron oxide, which is the kryptonite for any wet rotor circular. It doesn't matter who makes it, or ECM or standard type of technology. It doesn't make any difference. Black iron oxide kills pumps dead. In our standard 00 series pumps, we have what's called a biobarrier that is designed to filter out and prevent black iron oxide from getting into those circulators. This is something that's been constantly being upgraded in our 00 series pumps. It's one of the reasons why they last so long. The Bumblebee was tested for this particular issue for years before it was released. And again, a filtering system is designed to keep that stuff out as best it can. We didn't release the Bumblebee until we had that problem linked to our satisfaction. So one of the things Bruce said is cleaning the system obviously is a good thing, but black iron oxide just exists in water, and there's not much you can do about that. So what we've done is try to take that service issue away. I hope that answers your question. Bruce, have you seen anything to add on that one?
What we're starting to see now is that iron oxide problem showing up in the condensing boilers, and I think as time goes on, as we learn more, we're going to find that we need to address that issue. Remember, you got to remember, this is European technology for the most part. These condensing boilers will all come out of Europe, and the systems in Europe are very different than what we have here. They treat their water. They don't have iron, cast iron, and steel. They have PEX and aluminum and stainless. They don't have cast iron and steel and copper and brass and everything else that we have in our system. So we bring those boilers over here and hook them up to these systems and put that water through, which is loaded with the iron oxide. I think what we're going to see is some negative effects on those boilers inside the boilers down the road. I think that's the chickens have not come home to roost on that issue yet, and I think what we're going to have to do is start thinking about treating the water. And I think that's the next big thing that we're going to see. So.
Jerry Vanderwalker asked about a good brand of an electronic combustion analyzer.
Oh my goodness, there's just so many of them out there. Wohler, Bacharach, those are your higher end ones, and then you have the lesser expensive ones. There's UEI is another one. I think Wohler is probably the highest tech and addresses most of the issues. That's probably one of the best that's out there. It comes out of Germany. Really good analyzer, and Bacharach is made here in this country. I think those are the two most popular ones.
Very good.
Hard to say who's the best, but.
A ton of them. Well, full disclosure, Bruce's company reps Wohler, so we know where we're coming
from. Yeah, well, yeah, gee, gratuitous self-promotion. What can I say?
There you go. That's the best kind of self-promotion. Okay, with a ModCon boiler, is it better to add a small tank for thermal mass to the system? Asks Ray Sichinski. I hope I pronounced that properly, Ray. Chris, you're talking about a buffer tank, and I'll jump in and say, yeah, absolutely. Short cycling is a fact of life with ModCon boilers because they have such low water content. Adding a small tank really helps. If you look at it this way, a small tank is really the same as a big hydraulic separator or a big low-loss header. They do the exact same thing. The more water you have, the better off you are.
And your system is feeding off that tank. So, and again, we're back to the boiler that isn't running is the most efficient boiler. So we get a long on cycle and we get a long off cycle. And now the system is feeding off that buffer tank. It's absolutely a great idea, and it's not utilized anywhere near enough when we see people putting these little boilers with a gallon of water in them, hooking them up to systems with 25 and 30 gallons of water in them.
Very good. A lot of good questions here. We're not going anywhere for a while.
I'm here.
Cost of a Bumblebee versus a 007, asked Jim Price. We stay out of field pricing. I'm going to tell you it's probably about double. What is the life of a Bumblebee versus a 007? I mean, 007s, as you heard Anthony say earlier, he had his 007 in his house for a good, 20, 25 years, something like that. I mean, that thing had last a long time. 007 is a great circulator. The life of a Bumblebee, I mean, we've had them out for about a year. So it's hard to estimate. We've done our long-term cycle testing, and we would not have released unless we were very confident in its ability to last. I can't give you a comparison other than I think there's no reason to think that in a properly maintained system it shouldn't last as long as a 007. I mean, that's kind of the standard line, but there's no reason to think that.
Well, we tested them for 2 years, right, before they were released.
Yeah, so. I've had mine in my house for a couple of years. It's been running like a champ. Here's a question about the PC700. Will a PC700 control work with a boiler that already has an older Beckett heat manager on the burner? There's a good question.
Well, you got
fight each other, wouldn't they?
Clashing technologies, yeah, clashing technologies. It's either one or the other. I mean, the heat manager is an inferential control, which is counting cycles. It's looking at the cycles, the circulator, the cycles of the burner, and it's making a determination on how the boiler should run. A PC700 is an outdoor reset. So it's I think they'd fight each other.
Yeah,
I wouldn't. It's either one or the other. I mean, you can't do both.
I think that makes sense. George Gray asked a question. With primary secondary piping, is it necessary or advantageous to use all variable speed circulators, or can you just use one for the primary pump? I think either or. I think you could use it for just the primary circulator. It makes a lot of sense there. You could use it for both the primary circulators and your secondary circulators for heat delivery, depending upon what you have out there. I don't think they'll fight each other, but I think that the more you have on that kind of a system, the better it'll perform. But it's not necessarily one or the other. You could do both, or you could do one or the other. You could put a fixed speed circulator on the primary and use variable speed circulators on your delivery where it's going to do the most good, or you could do both. Again, it's kind of up to you, George, I think. There's no downside here, I guess, to using more of them. I guess.
Yeah, the pump's going to react to the BTUs that are being drawn out of the system. It's as simple as that. That's really what it's doing. It's reacting to the load changes. If you really think about it, the building is reacting to the temperature outside, and now the system is reacting to that, and the pump is reacting to what the system is taking out. The system, it needs more at sometimes or less BTUs, and the pump has the ability to feel that. It feels it. And it's simply by looking at the delta T. If the system is extracting more BTUs, then the delta T is going to increase. If the system is extracting less BTUs, the delta T is going to decrease, and the pump reacts to that.
Very good, very good. Louis Salikas from, I think, Louis, you're from Long Island, aren't you? Who sells these low-temp baseboard emitters? Bruce, it's called Heating Edge, correct?
It's called Heating Edge, yeah. We rep it. I mean, it's any wholesaler that does business with us can certainly get it. We don't do any business on Long Island, but Wales Derby does, I believe. And but it's called Heating Edge. You can, if you go to our website, you can get some information on it. Go to www.emersonswan.com. If you can read the fine print, it's down there in the lower left, and you'd be able to navigate to that and get some more information on the Heating Edge. But I know wholesalers in our operating area can sell it. So any wholesaler that does business with us has, and that's all of them, have access to it. But you could certainly get it. I mean, that would be easy. If you're a wholesaler, your rep calls us, we could do it. You know how those things work.
There you go.
We get it.
House just wanted to let us know that it's 86 degrees and sunny in Toronto.
Nice.
Today. Not hockey weather, but they don't have to worry about that up in Toronto right now, do they? Sorry.
Our Canadian buddies.
I'm telling you. All right. Okay, very good. Eileen Barrett would like you to contact her, Bruce, about conducting a training this summer at their Princeton office for their 20-plus team. So very good.
Yeah, Eileen, send me an email, bmarshall@emersonswan.com, and we'll see what we can do. bmarshall with 2 L's at emersonswan.com.
And there's a point from Brian Frederick out in, Brian, you're out in Alaska, as I recall. In most systems, since you shouldn't have to add water unless there's a leak, then isn't the only water you have to worry about is when you first fill the system? Yep, absolutely. That's the stuff you got to treat. And the thing about treating water is this, I have found anyway, and correct me if I'm wrong, Bruce, if your experience is any different, is water doesn't stay the same. It changes, especially if you have additives in it.
Absolutely.
Particularly glycol. The more glycol you have in it, the more corrosive it gets. And if it's a cast iron boiler, what does it corrode? Cast iron. There's your black iron oxide.
It's amazing how fast it starts too. We did a little science experiment a few weeks ago. We took a little mason jar, filled it with tap water, and we have pretty good tap water here in eastern Massachusetts. We have, we're paying for it, of course, but it's as water goes, it's pretty good. And we put a cast iron coupling, little 3/8 cast iron coupling, a steel nail, and a copper elbow. And we dropped it in the water, put the cover on, and within hours, little flecks were starting to appear. 24 hours later, the water was orange. It was absolutely amazing. It was, and this is just tap water. So this is a small example of what's going on out in your system. You fill your system up and you turn it on, and you forget about it. You don't even, nobody even thinks about what's going on inside that system, and all kinds of things are going on. And that's just, this is with tap water on a municipal system. Now you go to out into the country and you've got wells where you have all kinds of things coming out of the ground in the water. It's all chemistry, and it's again, it's an issue that you have. Someday, at some point down the road, I think the boiler manufacturers are going to start telling you to treat the water. In fact, I think a couple of them already are. They're saying you treat the water or your warranty is voided.
Right. I had a question to ask you. This is just a side note to David Williams. David, if you could email me at johbar@taco-hvac.com regarding your question or your offer here. I'd like to talk to you about that. So just so if you have that. Very good. Are we going to get some sunglasses and music at the end of this? No, don't have any music for the. I could put something up, but my sunglasses are in the car, so I can't do that. Guys, we still got about 56 of you still online. So if you have any more questions, again, this open up to any topic you want. If you want to talk about the Bruins Penguins series, or anything else you'd like to talk about, get some stuff. Get your questions in. Derek, good to see you, Mr. Lee. Hope your snow's gone way up there in the northwest kingdom of Minnesota. Travis, as always, go Bruins. But yeah, guys, any more questions you have, please get them in now, and we'll be happy to address them. Unless Bruce, you have a pressing engagement that you have to get to.
Dinner at 7, but I have time.
There you go. There you go. And actually, I was kind of half joking with Derek, because he just texted in, the last pile of snow melted just last week.
Where is he?
I love Minnesota.
Minnesota, oh, worst weather in the country.
Well, so far this year, yeah, we had down here in the Twin Cities, we had about 9 or 10 inches of snow on May 2nd, and we hit triple digits on May 14th. Go figure.
Yeah, crazy. I thought we had temperature swings. Wow.
Oh, it was just it's been nuts, and now it's thunderstorm season. So, all right.
Well, it's like here in Massachusetts, it's like we flicked a switch. My heat was running yesterday morning. My air conditioning is running today. It's 88 degrees right now. Yesterday morning it was 42. It's like crazy.
I don't know. Travis asked about the new Innovation Center. It's a beautiful facility, Travis. Great tiered classroom, and we have several other smaller classrooms as well for both internal training and customers. We bring tons of customers through there. Our first factory training class of 2013 is actually going to be the end of June. So please keep your eyes and ears open on the website for information on that if you'd like to attend. We have an updated program for this year. It's called Residential Hydronics, Advanced Soup to Variable Speed Nuts. So it's a 2-day program at the Innovation Center, and we'll have a really good time. We're going to talk about a lot of interesting stuff. So hope if you get the opportunity, hope you can come on down and see that. And yes, we will still go to Dave & Buster's, for that is a lot of fun. Question from Louis, does it matter hunting for the BTU rating on a ModCon boiler since they now vary from 80,000 to 300,000? Hunting meaning getting something that's as close to the right size as possible. I still think so. Even though they do modulate, they have limits on how much they modulate. They have their turn down ratios. So getting something as close as you can get to what you need, I think obviously that's the best way to go. Because again, these things, short cycling is a fact of life with ModCons, but we'd like to keep it we'd like to make sure it short cycles as little as possible, and it's priced right, obviously.
I had that conversation with a guy a couple of weeks ago that he was going to put a 100,000 BTU boiler in, and the load on the building was 75,000, and he wanted to know, was that a problem? And I don't think it is, because again, the boiler will modulate down. It's a 5-to-1 turn down. So, the boiler can go down to 80,000, it can go to 60,000. It's only going to modulate to the load. It'll probably never fire to the 100,000. So it doesn't hurt to do that. You just don't want to vastly oversize it, you know.
Right.
Go a
And
little
then
bit over.
you also take into account your domestic hot water load if you have an indirect. And we did our webinar on that. So go to the neighborhood and you can view that webinar and see how the size of the boiler makes a difference in how the output of an indirect hot water tank. Dennis Alzuski, I hope I pronounced that properly, Dennis, asked, what type of additives do you recommend to treat boiler water? I'll plead marginal ignorance on that one. I don't. Bruce, do you have some information you can share on that?
There are several. There are a couple of things that you really need to do. You have to I don't want to. We're getting ready to rep a product, but I really can't talk about it just yet because it's not totally official. But the thing you really the two things that you want to address are the iron oxide that is in the system, and there are products that will address that. They're basically magnets that filter it out. It's almost like a Y strainer type of thing that will filter out the iron oxide on an ongoing basis, and then you can remove it from the system. And the other thing is the pH. You really need to look at the pH of the water in the system, and that changes. And you need to put additives in which will raise or lower the pH. You have to get to a certain point. 7 is pretty neutral, and that's really what they're looking to get to. So those are the two things that we really think that you're going to have to address: pH of the water and the iron oxide issues. Those seem to be the two pressing issues.
There you go. Dennis, I hope that addressed your question. Brian came back. If you have an indirect on priority, why would the BTU load matter as the rest of the system is down? Well, the BTU output of the boiler directly impacts the rate of recovery of the indirect. It just depends on the load of, the size of the tank. It depends on how, what you need for domestic hot water, what's the flow rate of your fixtures, etc., and what kind of a temperature rise you're dealing with. So there's a lot of different things at play there. Again, we don't want to rehash our previous webinar. I do encourage you, Brian, to go into the neighborhood and view that. That'll help you figure it out, or maybe help you explain some of this. But most indirect, and I learned this from Bruce because Bruce is the smartest man I know. That the output of any indirect, the rated output of an indirect, is based on certain assumptions of BTU boiler output. Generally, 145,000 to 180,000 BTU output. That's where you get the ratings on the spec sheet. If the boiler is significantly smaller than that, the ratings are not going to be the same. They're going to be considerably lower, and you have to be able to reconcile the two. You may with a 75,000 BTU boiler, you may very well, with when you look at the storage of the tank, the recovery at that 75,000 BTU rate, and the flow rate of the fixtures and the temperature of the fixtures, you may very well be fine most of the time, but you may run into that perfect storm where you run a tank dry inside of 12 minutes. It just depends. So it's always good to know the math, do the math so you know where you're at. So in that, I guess, I don't know if that answered your question, Brian, but that's why it matters.
And you size to the maximum load also. What's the biggest load? Is it the heat or the indirect? And you size for that.
Exactly. So there's always things to take into account there. So I hope that answered your question. Setback of inside temperature can be a money saver. I am getting a lot of info from my suppliers that we need to sell these thermostats. What temp do you feel a nighttime setback is efficient, or do you feel this is really not a great low-tech component to add to a low-tech system? Asked Curtis Reynolds. Good question.
Great question.
My feeling on setback thermostat is when you apply it properly, it'll save you some dough. I've always felt that, no more than 3 to 5 degrees worth of setback for no less than 6 to 8 hours saves money.
I agree with that.
If you go for a greater setback for a shorter amount of time, it goes back to something my Italian grandmother used to say. She says, Giovanni, it's easier to clean a room than it is to clean a dirty room. So by the same token, I apply that same logic because my grandmother was maybe the second smartest person I've ever known. It's easier to heat a warm room than it is to heat a cold room. So I look at it this way: if you set it back, okay, so I'm going out to the grocery store for an hour. I'm going to turn this thermostat down 20 degrees. Why keep the house warm when nobody's in it? Well, that's certainly, you're not going to use any fuel as much fuel while you're gone, but you got to get that room back up to where it's comfortable, and that's when you start to use some fuel, in my opinion.
I think the speed that the system generates heat is key to setback. The slower the system generates heat, the less you should use a setback. And I'll use an extreme example: a radiant system. You should never set back a radiant system because it takes so long for it to recover. Now take the other end of the spectrum, a warm air system. It's pretty fast recovery, so you can set back a little bit more with a warm air system because it reacts much quicker. So there's your opposite ends of the spectrum. But I think that if you're going to do something like outdoor reset and variable speed pumping, you don't want to add a setback thermostat to that, because remember, we're not slamming a lot of BTUs into the system. You remember that we spread out the delta T, so it's going to be a more gentle form of heat. You're not going to notice a big difference. You're just going to be comfortable. You're going to be warm. But if you go to a setback now, you've lost. It's going to take longer to get that temperature back up in the building. So I would not. I would almost view that as clashing technologies.
Unless I think if your setback was modest, I think for a long period of time, small setback, again 3 degrees maybe.
Yeah.
3 to 5 degrees for no less than 6 to 8 hours, and then intelligent recovery is also, I think, the key here. Where if I want it to be X degrees at 7 a.m., I want it to turn on at say 6 or 6:30.
Mm-hmm. But it was off between midnight and 6, so you were at a lower temperature. Yes, that will save some money. Yes.
Yeah, I think it's again the biggest issue I've seen with, there's two things I've seen with setback thermostats is they're a great idea, but once you get them installed, there's not a person on the freaking planet that can program these things intelligently or effectively, because they're like, could they possibly make these things more complicated? That's, I think, one of the great promises of that the Nest thermostat that kind of did its thinking for you, based on motion sensing. Okay, I get that technology. Keep it simple. But the whole theory behind the guys that developed the Nest was that there's all these setback thermostats that nobody uses because nobody can figure them out. So most of them are installed and just bypassed anyway. People just tend to set it and forget it. So there's two schools of thought here. I personally, in the wintertime, I leave my thermostat at 68 degrees, day and night, and I have no complaints about my fuel bills. Setting it back, I don't think would save me much at all.
We had a case this past winter of a church. They put a setback thermostat in and set it back to 55 degrees, and then had it come on Sunday morning at 5 o'clock, thinking that it was going to be 68 degrees by the time that people got to the church. Well, it was barely up to 60. And, it takes time to recover. You have this huge setback, and they expect to gain the 20, it was from 55 to 68. It's just not going to happen right away. So, and they were complaining that it was cold, and, you set it back too much. So.
Yeah, a follow-up question from Nick Sarandu about will a cast iron boiler work well with setback? I think cast iron boiler will be fine. It's the delivery portion, how quickly they respond to the delivery portion, that we'd be most concerned about.
Right, it's the delivery. It's the speed of it's the speed that the system recovers from that. Remember, you're heating the air in the building. You're heating the air, and so you lose that many degrees. If you set it back to 8 or 10 degrees, well, then you've got to recover that. And to me, it's the law of diminishing returns, that everything you saved, you put back in plus in getting it back up to the comfortable temperature.
Right. Again, moderation is the key here. Again, no more than 3 to 5 degrees, no less than 6 to 8 hours. Then I think it makes some sense. And again, if you're going away on vacation for 2 weeks, well, duh, that's a gimme. But So setback's one of those interesting things. It's a great concept. It gets applied kind of poorly. Here's a good question from Louis down at Long Island, I believe that's Louis. Would a two-stage thermostat wired to the TT do the same money savings? You know what? I'm going to take that and run a different direction with it, Louis. Poor man's reset is a two-stage thermostat. Really is poor man's reset. If you think about it, stage 1 should be wired to your circulators to turn your pumps on and off. And this is if you have a cast iron, large mass cast iron boiler. So Low mass boilers just don't do this. But a two-stage thermostat, stage one turns on your circulators, and then stage two, when you can't keep up, then we fire the boiler. And that acts like a poor man's outdoor reset. It's not the same as outdoor reset, not as effective as outdoor reset, but it's a step in the right direction where you can have, you take advantage of the residual heat in the boiler as best you can, and when you can't keep up, then you make the boiler do a little bit of work. The concern with a two-stage thermostat is the droop. If it doesn't anticipate, if it doesn't turn on until you're already uncomfortable, well, then you're going to go through a series of you're going to go through a time frame of being uncomfortably cool before the system can get back going. So there's the drawback of a two-stage thermostat doing this. The advantage of it, it's a very simple thing to do. They call that poor man's reset. How long is the droop? It depends on when the boiler comes on, what the differential is on the two-stage thermostat, and the speed of the recovery, the speed of the delivery. So it really depends on how long it is, how long before the stage two kicks in, and then how quickly stage two can recover. So,
it might also be predicated upon having some heat in the boiler to start with, too.
Right.
You've got to, I like to think of that cast iron boiler as a flywheel. It's a storage. You've got all that mass, and you've got all that energy stored in the mass. So if it's there, but if it isn't there to begin with, then you've got that lag or that droop, that period in between where you've lost ground in the building. But if the energy is already there, then sure, it'll work fine. Bring on the pump, and maybe the burner doesn't even have to come on. You've used the stored energy that's in the mass.
Right. If you can satisfy the call for heat without ever turning the boiler on, well, it doesn't get any better than that.
Exactly. The boiler that's not running is really efficient.
Yeah, that's right. Just like the most efficient circulator is the one that's off. So
the one that's off.
All right. Isn't talking about heating fun, guys? I'm telling you. Talking about heat is fun.
There's just so much.
Yeah.
It never gets old, and it never gets boring.
Nope, definitely not. Definitely not. All righty. Well, guys, it's about 5:35 in the east, 4:35 here in the Midwest, and probably a different time where you are. I'm going to put out the last call for questions. If you have anything left, we've still got about 30 guys left online. So any last round up for questions. John Barber says thanks for the great info, and I still say you pronounce you spell your name wrong, John, or maybe I do, one of the two. I'm not sure. Curtis, it was good to see you in Hershey as well. That was a lot of fun, putting faces and names together. So I appreciate you stopping by the booth down in Hershey at I still call it the Neochim show, but I guess it's the OESP show. Doesn't roll off the tongue quite as nicely. So again, last call for questions. Going once. Going twice. I'll give you a little bit more time, maybe if you're typing furiously back on the other end.
If anybody's going to the Nephi show in a couple of weeks, I will be in the TACO booth on Wednesday. I believe that's if I'm not mistaken, is that the 12th? But I will be.
Yeah, I think so.
I will be in the TACO booth, pressing the flesh.
That's right, and we will have a big sign, the smartest man I know, right here. I'm going to get Patriots tickets out of you yet for that, Bruce, I'm telling you.
Oh, you got to come up here. We have massive tailgate parties.
I've been to your tailgate parties. They are a ton of fun.
Oh, yeah.
So, anyway, all righty, gang. Hey, thank you all for being here. We very much appreciate the gift of your time. And again, I hope this was a lot of fun. It sure was fun for us here on our end. I'll speak for myself, Bruce. I very much appreciate your being here as well.